Hello, I'm Dave Casler, amateur radio call sign KE0OG, your guide through the ARRL license manuals. The videos in this course follow the manuals section for section. You can get the ARRL license manuals from the source listed below the video. After you watch the video, dig into the corresponding section of the book, study the associated questions, and then come back for the next video. I'm Dave Casler, amateur radio call sign KE0OG. Hello and welcome to the amateur radio technician training videos. Okay, with this video, let's take a look at section 3.2 on components and units. It's easy to overthink this section, which is really rather simple. It introduces electrical components plus the concepts of reactance and resonance. The material I originally put together for this section several years ago still applies nicely, so let's watch that. What this section does is simply introduce you to some various components that are used in electronic circuits. And I think the text is quite clear, so what I'm going to do this evening is simply show you some examples of some of these circuit components actually on a circuit board in a real radio, and then show you how that correlates with the schematic diagram. We're looking at an actual circuit right now. This is the inside of a little Morse code transceiver for 10 megahertz, 30 meters. And I thought I'd show you some of the parts that we're talking about in this book in their native habitat. Let's just come in here a little bit and we can see some of these right here. This one, which you see right there, is a transistor, a single transistor. It's got 3 leads. I think you can just see them there. And these little things right here are resistors. And that thing right next to it is a diode. That is an electrolytic capacitor. These are capacitors that don't have any particular polarity. This right here is a small variable capacitor that is used only when setting up the radio. These things in these cans right here are crystals, and those crystals are made of quartz, and they oscillate at a certain frequency when hooked up with a resonant circuit. Now this right here is another variable capacitor, and this thing with the little green slot in the top of it is actually a transformer. It's 2 inductors back to back, and what happens is this is used as part of resonant circuits on either side of a section of the radio here to move the signal from one side to the other. These great big capacitors here are electrolytic capacitors that are used as part of the power input to make sure that the voltages are very, very nice and smooth and don't have any AC components. You see these black things here. These are integrated circuits. They're not very big. You can see my fingertip as an example. And they're in, if you look very closely here, little sockets to where they can be plugged in and out. They could be soldered directly to the board. In some projects they are. Now, right here we're looking at an inductor, and this is really obviously an inductor. This is wire wound on a little ferrite core, certain number of turns, gives you a certain inductance. Now over here, this right here, I'm going to back up just a little bit. This is a variable capacitor. You see how the plates mesh and don't mesh, and so I can take it to the point where those plates are all the way out. That's at minimum capacitance, and then as I insert the plates here into between the other plates, that adds capacitance until you get all the way up to the maximum capacitance. And we use this as part of a resonant circuit to tune what frequency we want to use as we use the radio. Now these things right here are a combination of a potentiometer and a switch. And you can hear the switch as I turn it on. Okay, and then as I come up here, the wiper arm moves inside here to give me the amount of resistance I want. And you see right on top of it how it says, let's see, that's 10K, I think, 10,000 ohms, and that's the maximum. And you see the way the wires are connected right here. The center one is always the one that's attached to the wiper arm, and so as you turn this up, then this wiper arm moves closer to here, so the resistance across these decreases, and of course that means the resistance across these increase, so that you have the same amount of resistance from the beginning to the end. Okay, so lots of fun little components. Now we have to be able to get signals in and out. This right here is an SO239 connector that's connected to the antenna, and you can see here on the inside where I have soldered the wire there and then down to the board where it's supposed to be. This, I'm going to turn this around here so you can see this. This is a transistor in a rather old-time package. It's used, I think, as part of the switching circuit to turn the thing on and off. But you get a very good idea of what these components are, what they look like in actual practice. I'll mention just one last item, and that's this thing encased in all these black fins. This right down here is the power output transistor, and the reason it's got that big heat sink on it is because it handles several watts of power, up to 5, and it creates some heat in the process of doing it. And that's a nice little tour of what the inside of this device looks like. Now here's another little project that I built. This thing is called the Warbler. It transmits on a single frequency in the 80 meter band, and it's designed for one purpose and one purpose only, and that is for PSK31. And you see many of the same components, the crystals, the power outputs with their heat sinks and so on, various connectors over here that you need. Now the question is, how does one put something like this together or even begin to understand what has to go into it? I had to solder each one of those little things there. And this particular board has something that we see right here called a surface mount device. It's a very, very small thing, as you can see from my finger. I had a hard time getting it in there. Now, in order to tell what's actually going on, I mean, we could look at the diagram that I used to wire it. This is what came with the kit. It's kind of an exploded view of the circuit board, and it shows me what to put where, but I still don't really understand it. So what comes with it is the schematic diagram. Now this is the schematic diagram for this little transmitter, and I'm just going to point out some of the symbols here. When you have a schematic, this, for example, right here is the input circuit that keys the transmitter. These plates, just like this, that you see right here, are a capacitor, and it's actually reminiscent of what you saw, what I showed you earlier, what a capacitor looked like, plates together. Now, that one that I showed you with the plates meshing was an air variable capacitor. Capacitors don't have to have a dielectric that's made of air. It can be some other thing. A resistor is just what you might think here. This kind of squiggle in the line just represents that it's resisting the flow of current. And in the schematic diagram, we put in here the number that goes with it, R26, so we can find it on the circuit board, and it's a 22,000 ohm resistor. This symbol right here is a very common symbol for chassis ground. In fact, here it just shows a regular earth ground, which is very common. These triangle shapes right here are integrated circuits. This is a special kind of integrated circuit that's an amplifier, an LM393. And when we see this U4A, well, U4, as it turns out, has several different parts. And so we can take over here where we see U4B. These two happen to be in the same package, physical package, but you can see the different pins, 1, 2, 3, 4, 5, 6, 7, and 8. And over here is where the power goes in. There's a diode right here that makes sure that we do not put the power on backwards. The power can only flow, the electricity, the current can only flow in the direction of the arrow. It cannot flow in the opposite direction. So since it's flowing from positive down to negative, we've got this diode here. If we accidentally reverse these, it won't flow and it won't burn out the integrated circuit. Here is a simple transistor. This one is a PNP because it's got the arrow up here. And these kinds of little symbols mean look for something else somewhere in the schematic diagram that's got that same one, and that's what it's connected to. This right here, we're actually looking at turning something on and off. This is an FET, or field effect transistor right here. See, in the bipolar transistors they touch, and here they don't touch. This just, if there's a voltage here, it will allow the current to go through, or it will turn it off. And so the big integrated circuit is this one right here. Integrated circuits usually have a U, and this one has all the pinouts. As it turns out, this has got essentially most of a radio in it. The Y's, for whatever reason, no one knows why, are crystals. And you can see kind of a little bit of an indication here of something in between two plates. When you see that, that's actually a piece of quartz that's ground so that when you put electricity on either side of it, it actually vibrates at the fundamental frequency of the crystal, just like you would with a tuning fork, except at much higher rates. Now you occasionally see something like this, two diodes back to back. Wouldn't you think that that would just completely short the thing out? Well, as it turns out, you need to get about 7/10 of a volt higher on this side than this side before it will conduct. Similarly here, so this is leaving a little window in between, and it serves to limit the incoming signal. There again is our little inductor, probably one of those toroids, and in other places there are all different kinds of things. So I'll just show this to you upside down because it's where the camera happens to be pointed here, but you see the transformer here. This is an inductor, and this is an inductor, and they're put so close together that they're in each other's magnetic field. So if the current here changes, the current here will change too. If you have a few turns here and many turns here, the voltage will be up here and the current down. It's a very convenient way of handling AC. So that's a real schematic for a real radio. Now there's just one particular thing that's in this section that's a little different than simply introducing you to some tiny little things, and that is the idea of resonance. And you're familiar with this concept. If you hit a crystal glass or something like that, it'll ring at a particular tone. If you pour a little water in it, you've got more mass there, so the tone goes down, just like we saw when we were doing the organ and the piano. Well, as it turns out, the way resonance works in radio is we have two kinds of components, a capacitor and an inductor. And as it turns out, they are opposite each other in the way that they store energy. If you apply a current to a capacitor, the voltage starts to go up on the capacitor till it reaches the limit that the supply has. If you apply a voltage to an inductor, the current starts to go up until it meets the amount of current that's available in the power supply. Now, as it turns out, they do these things kind of opposite to each other. So if you hook up an inductor and a capacitor in parallel, what they do is they swap energy. The capacitor charges, and as it discharges, it charges the inductor, and as the inductor discharges, it charges the capacitor, and this goes back and forth at a very predictable rate. And this, in fact, is how we create RF energy. We choose the component values so that it does that back and forth thing at the frequency we want. It can be many millions of cycles per second. As a matter of fact, it can be billions. In your computer, you've got a quartz oscillator that has got a little piece of quartz between two plates that helps regulate very precisely how that energy goes back and forth. And that's called resonance. Sometimes the inductor plus the capacitor together are called a tank circuit because they, like a tank, they hold energy. And then you can put a little amplifier off of that thing that just watches how it goes back and forth and make a strong signal to transmit. That's really all there is to resonance. The key thing to remember is that the component values, the amount of inductance and the amount of capacitance, will determine the resonant frequency by very, very well established formulas. Not something you need to worry about right now. I think what's in the book is perfectly adequate. So I'll let you get to studying your book. Be sure to share on social media that you're learning about ham radio. You may find several friends who are doing the same. Thanks for following along with the videos and the book. After you've studied this section in the manual and are satisfied you understand the questions and their answers, come back here for the next video. The ARRL is the National Association for Amateur Radio, and I urge you to join, even if you don't have your license yet. That way you get QST, the League's monthly magazine full of articles for beginners and veterans alike, or you can choose On the Air, a magazine designed specifically for those new to amateur radio. Until we next meet, 73.